Hello everyone, my name is Samuel Remedios, and I'm going to talk about self-supervised super resolution of MR images with slice gap. Automated processing algorithms often require isotropic resolution of their input volumes, isotropic meaning the same resolution in all axes. However, we're interested in the automated processing of clinical 2D acquired magnetic resonance images, which are volumes constructed by acquiring and stacking consecutive 2D slices. These slices have an associated thickness and separation, and when the separation is greater than the thickness, the volume has slice gap. This happens commonly enough that we have a notation for it. This is read T skip G for a thickness of T millimeters and a gap of G millimeters. Since these volumes don't have the same resolution in all three cardinal axes, we call them anisotropic. Here, we show an axial and sagittal slice from a volume, which is isotropic on the left, and one from a 4 skip 1.2 volume on the right. The sagittal view is through plane in this case, and was rendered with nearest neighbor interpolation to better visualize the resolution differences. Since we need to process these images, our job is to improve the through plane resolution. Super resolution methods estimate high resolution images from low resolution ones. The contemporary way to do this is to train a data-driven model, a neural net, on paired low resolution, high resolution data, then apply the model at inference time. This can be done at the slice level or patch level. Commonly, the way to get paired high-resolution, low-resolution data is to acquire high-resolution data and degrade it according to an observation model. And our observation model is pictured here. We take a high-resolution signal, a blue square, and convolve it with a blur kernel depicted here. We might call this blur kernel H in future slides, and the full width half max of H simulates the slice thickness. So here's the high-resolution data, and then we blur it in one direction with our blur kernel, and then we downsample it with the cubic B-spline interpolation, and that simulates the slice separation. So if the thickness of H is less than the downsampling rate, we've also modeled slice gap. And we'll also often render these images with nearest neighbor interpolation like this. However, what high-resolution signals should we collect? How should we select the data set for this task in general? As we know with deep networks in medical imaging, we can see a domain shift in image contrast, scanner effects, anatomy, pathology, and even resolution. So one solution to this is to use zero-shot self-supervision. So, since the in-plane data of an anisotropic volume is relatively high resolution, that can serve as our target in supervised learning. This allows us to match contrast, anatomy to an extent, and pathology between the training and inference time data sets. And since our goal is also isotropy, we know exactly the slice separation to simulate. This allows us to match the resolution distributions as well. Now that we have paired low resolution and high resolution data, we can do supervised learning. So those methods I just talked about were presented in a previous work called SMORE. However, there was room for improvement, and those enumerate our contributions today. So first, SMORE assumed that H, the blur kernel, had a Gaussian shape. Our method leverages a technique called espresso, which is a self-supervised technique to estimate a relative blur kernel between the in-plane and through-plane of an anisotropic volume. SMORE also assumed that the full width half max of H was equal to the slice separation, which meant that there was no modeling for slice gaps. Since our H is learned with espresso, it also models the slice thickness, and therefore models slice gap too. SMORE also achieved its best performance with pre-trained weights and leveraged transfer learning, so it was not fully zero-shot nor self-supervised. This is a drawback for scenarios when the low-resolution volumes come from a different distribution as the training data set, like if we wanted to super resolve a different body part or a novel contrast. By contrast, our method trains from scratch. SMORE also used the EDSR network, which at the time was a state-of-the-art choice, but deep learning moves so fast and more architectures have been proposed since then, and we've updated to the WDSR network. SMORE also trained two separate neural networks. One did anti-aliasing and one did super resolution. These networks were trained independently but applied sequentially. This led to better perceptual results, but we noticed that the images exhibited over-sharpening in some regions, and we'll show that later in this talk. To address this, we reduced this down to a single network and no longer saw the over-sharpening artifacts in the results. Finally, SMORE was trained with a fixed patch size. Regardless of the slice thickness and gap, a fixed patch size was used. This means that, for example, a patch size of 32 by 32 for a 6-skip2 image would only have 4 pixels of context after degradation in a single direction. To address this, we adopt a dynamic patch size defined in a low-resolution space. So we choose 48 by 48 as our patch size, and if we have that same 6-skip2 image, we would still have 48 pixels of context, but the high-resolution patch will be of dimension 384. So these summarize our alterations to SMORE, and as we'll show, these improvements to the results, are substantial. But first, we're going to do a quick graphical overview of our method. Again, we're zero-shot and we're self-supervised. Zero-shot meaning no external training data, and self-supervised because we simulate our own paired data. So first, here, as it indicated, we use espresso to estimate the blur kernel H. This models the slice thickness and the shape of the point spread function and allows us to model low-resolution data from high-resolution data. Second, we extract patches that are relatively high resolution from the in-plane data. With those patches, and with our observation models before, we can blur and downsample the data to create low-resolution data. And now we have paired data, and we can train our neural network, the WDSR model, in a supervised fashion. Finally, once the model is trained, we can extract through-plane slices from both cardinal through-plane directions, and then independently super-resolve them. We then restack these slices into their corresponding volumes and average them to achieve our final result. To validate our method, we've designed an experiment where we had a ground truth. We took 50 subjects from the OASIS 3 dataset, all isotropic and high resolution, and simulated their low resolution counterparts using the observation model mentioned before. Then, we took the low resolution data and ran them through a method, like this, including competing methods and our proposed one, to obtain a super result volume. We then ran this volume through SLANT, a pre-trained deep network for brain region segmentation, and this results in a label volume of the super resolved image. To get some quantitative measures, we can now run our ground truth isotropic image through SLANT as well. And now we can compare the signal recovery between the super resolved and the true volumes, as well as the consistency of the downstream task with the dice score coefficient. Let's take a look at the qualitative results first. On the far left here, we have a mid-sagittal slice of a representative subject at 4-skip1.2. The top row is the image domain, and the bottom row is a log scale Fourier magnitude. The far right shows the ground truth. First, let's go back one. First, let's take a look at a baseline result, cubic B-spline. We can see that the aliasing is still present in the image domain, and we haven't recovered any of the high-frequency information in the Fourier domain. Next, here's SynthSR, a new super-resolution technique which maps any head or brain to a T1-weighted isotropic space. While the method does achieve visually pleasing isotropic features, we can see that the contrast of the skull is not quite right, nor did we accurately recover non-brain regions. Furthermore, if we look in the Fourier domain, we've lost some high-frequency data in the anterior-posterior axis. Here we have SMORE and also our method, which I want to show and talk about at the same time. We can see some of the aliasing artifacts still present in the skull, near the superior part of the head, which are addressed a little bit better in our method. This is likely due to the modeling of slice gap, and since slice gap leads to aliasing. Also, and this is a little subtle, but we can see the over-sharpening that I was talking about in the inferior regions of the head, down here, and in the brain in SMORE. And those are not present in our method, those hyper-intense regions. I do want to talk a little bit about the Fourier spectrums of these two approaches, SMORE and ours. Neither SMORE nor our method recover the high-frequency information out in the corners, and actually it seems that our method seems relatively darker out there. We hypothesize that some of SMORE's coefficients out there come from over-sharpening and uncorrected aliasing, both of which turned into high-frequency coefficients, just not the right kind. However, we are still interested in understanding better how we can appropriately address this. On this slide, for quantitative results, we used PSNR and SSIM to estimate how well we recovered the signal. Our experiment wasn't just at 4-skip1.2. We created 8 different resolution data sets based on common clinical resolutions that we often see. And for both PSNR and SSIM, our proposed approach outperforms all others. So here, we're looking at some dissimilarity coefficients between between the sum upsampled method and the truth after the downstream task across 4 regions of interest. Let's focus though only right now on one of them, the ventricles. Here we can see that which method corresponds to which color by the legend, and the resolutions are across the horizontal axis. In the case of the ventricles here, we can see that our method outperforms the others across the board. Now over here is the thalamus results. It's much closer here between our method and SMORE, and in some places we do not perform better than SMORE, like at 4 skip 1.2. You can see where the box plots are centered. Briefly, I'll reveal these other two, the cerebral white matter and cerebral gray matter. At a glance, we can see that our method outperforms the others at each resolution, and these plots can be inspected in further detail in the paper or in the poster. There is an interesting thing I want to show here. Let's take, for example, the ventricles again and consider a slice separation of 5 millimeters. So we'll block out everything else. This means 5 millimeters can show up as both 4 skip 1 and 5 skip 0, if that's the same slice separation. SMORE sees a degradation in performance when slice gap is present, but ours does not. So here these lines line up, and we can see that we're fairly robust with a 1 millimeter gap with our method, but SMORE's drops by a bit. So, in conclusion, we have presented a truly zero-shot self-supervised super resolution method. We incorporate a model of slice profile shape and thickness, and this allows us to address slice gap in 2D MRI. Signal recovery results and downstream performance results were strong. Our code is open source and available at this QR code. I want to thank all of our funding sources and co-authors, and thank you for listening.